Okay, let's start. So as I told you last time, we will be dedicating this 2 or 3 lecture hours to the climate change problem. And that's a very good time to present this problem because we have seen the mechanism in the ocean which are driving the general circulation, which are driving some short-term processes, and therefore now by analyzing the climate change aspect or the climate change problem, we will see how these variations of the climate are reflected into the ocean circulation and ocean state of the ocean state. First of all, let's see what is the definition of climate, because you have heard rather often climate and weather. There are two subjects which are we rather often talk about it. Here in Italy, but I don't know in your countries, but there rather often they do the confusion between climate and weather. The climate is completely different than weather, and the climate is something which represents the average, a long-term average of weather conditions. Weather conditions is instantaneous situation, instantaneous state of the atmosphere, while the climate is a long-term change of the weather. So long-term average of weather. So we are talking about the continental climate, coast, and so forth, different type of climate, which are really the average of a long-term average of the weather conditions. Typically, once upon a time, the definition of climate was as an average of 30 years of weather conditions over in a certain area. And there is one thing what they say, what it says, Sir Robert Heinlein. He said, climate is what you expect, and weather is what you get. So you expect something which is the average weather, and the weather is what is right now. Right now we have a clear sky, we have no wind, and so forth. But if you want to talk about the climate the climatic conditions of the month of April, in that case we should do the average of all the wind characteristics and so forth, and then we got a number which represents the average of that specific month or the specific year. So this is one thing, and you always have to take into consideration this thing. And so, but when we are talking about the climate is not really constant. It's really changes on a long time scale. And why are we talking now too much about the climate change? Because the climate change becomes a very important topic since the beginning of the industrial era, when the humanity starts to impact the climate in an important measure, and therefore now we are talking about the climate, but there are two aspects of the climate. One is natural climate changes, which are due to the long-term changes of characteristics of the atmosphere and the ocean, not a 30-year, but certainly much longer than that. But then we are talking about the long-term changes, climate changes induced by the activity of man. And this activity of man typically generates the trend. So long-term trend or increase or decrease or some parameters of the atmosphere of the ocean are partly partly due to the action of man, to the industrial activity, to other activities of man. We will be looking and seeing during these 2-3 hours. We'll be looking at various aspects of the climate change, starting from the atmosphere, ocean, and then how this reflects into the biological aspect, the biological component of the ocean, and obviously also on the earth, on the land. But we will be mainly concerned, and we will be mainly addressing the problem of climate change and the ocean. So the most important thing is that that we live in a greenhouse. That we live on Earth, which is in a greenhouse environment. So that means that, as you remember when I was talking about the heat budget on the Earth, that one part of the not complete part of heat which is accumulated at the Earth is lost into space due to a certain temperature of the Earth, but about the only part of this is lost. Sorry. This is. No, sorry. I have some problem with my mouse, which sometimes. Okay, here it is. So let's go back. So we live on Earth, where we have the atmosphere has greenhouse gases. These greenhouse gases have a role to absorb part of the radiated upward energy which has been accumulated at the Earth. This is the typically infrared radiation, and this radiation has been absorbed by greenhouse effects, by greenhouse gases, and about 90% of this heat is then absorbed by the greenhouse gases and then radiated back toward the toward the Earth's surface. So that means that thanks to greenhouse gases and thanks to the greenhouse atmosphere, the Earth or the atmosphere is warmer than it would be without greenhouse gases. For that to illustrate this, you have the two examples of the planet on our on the sun here and near to us, which is one is planet Mars, has a very thin atmosphere, nearly all carbon dioxide. And because of the low atmospheric pressure with little to no methane or water vapor, which are greenhouse gases, Mars has a largely frozen surface that shows no evidence of life. Why it has a frozen surface? It has frozen surface because the heat, which is eventually absorbed in the Earth, in the Mars surface, is lost by the infrared heat radiation. Therefore, there are no greenhouse gases which would keep this heat energy which is lost in the space. Another example is too much greenhouse gases, which is the Venus. But it has also all carbon dioxide, but the Venus has about 154 times as much carbon dioxide in its atmosphere as Earth. That means that it has a large concentration of greenhouse gases, enormous concentration of greenhouse gases, producing the almost complete absorption and radiation of the heat obtained from the Venus surface, and so all this heat, or a large percentage of this heat, is kept in the atmosphere of the Venus. Therefore, the Venus has a very high temperature. So these are two extreme cases where one planet has not enough greenhouse gases or too much greenhouse gases, and consequently not enough greenhouse effect or too much or too strong greenhouse effect. So this is why the Earth is the good place to live in, because it has a right temperature to support the life. And so, as I told you, I think I mentioned it to you before, that without greenhouse gases, or with the lower concentration of greenhouse gases, the Earth temperature, average Earth temperature, will be minus 2-3 degrees, while with the greenhouse gases of this concentration, what we have really now, it's about 15 degrees above zero. So you can, but I'm talking about the average temperature. If you do the average over the entire atmosphere, the average atmosphere temperature, the average surface temperature of the Earth is around 15 degrees, which is, I'm talking about the average in time and space. So then this is the appropriate temperature or good temperature to support life. So that's one important concept. The temperature of the Earth depends on the solar activity, because as we have seen and mentioning before, the only heat which comes and which is heating the surface is the heat coming from the sun. Therefore, the heat reaching the Earth depends mainly on the solar irradiance. And here you can see that the solar irradiance, this heavy yellow line is the average, the running average of these thin yellow line, which is the solar activity. And solar activity has a period of around 11 years. And this you can see these peaks. If you do the long-term average, you obtain this heavy yellow line. And you can see that the solar activity changes on a long-term time scale. This is from 1880 to 2020. And Earth temperature more or less follows what is happening in a solar activity up to a certain time, mainly around mid-90s, last century. Before, it was more or less parallel one to another. Obviously, not all signals what you see in solar activity is not present in a sea surface temperature, or in a temperature, because the temperature doesn't depend at the Earth only on the solar activity. It depends also on the volcano eruption, depends on a large number of factors which are determining the amount of solar energy which reaches the Earth's surface. However, strange thing happens in mid last century, when there is this divergence between what is happening in the Earth temperature, and in the solar activity. Earth temperature starts to increase rather strongly, and you can see that between 1950 and nowadays, there is an increase of temperature of around 1 degree Celsius. while at the same time there is no any important changes of the solar activity. And this is the signal which we should connect, and we should interpret in terms of the reduction or increase of the greenhouse gases in the atmosphere. So increase of the greenhouse gases in the atmosphere means that the greenhouse gases are absorbing more energy, more long wave energy, which is radiated from the Earth, and then it radiates back this long wave energy to the Earth, and therefore there is a heating of the surface, and there is an increase of the temperature. So you can see how these greenhouse gases can be responsible. Changes of the concentration of the greenhouse gases are responsible for the changes of the temperature, although the solar activity becomes more or less at the same level. There are some changes, but not as important as temperature. And here is in words what I already showed you in a slide before. There are several lines of evidence which show that global warming cannot be explained in terms of changes in energy from the sun. So since 1750, more or less, the average amount of energy coming from the sun either remained constant or increased slightly. This is what we have seen before. But if the warming were caused by a more active sun, then scientists would expect to see warmer temperature in all layers of the atmosphere. Instead, they have observed the cooling of the upper atmosphere and a warming at the surface and in the lower parts of the atmosphere. Why is this so? This is because as I told you before, the greenhouse gases, which are in the lower atmosphere, they are trapping the heat, and they are radiating the heat back to the Earth's surface. Therefore, the lower atmosphere becomes warmer because there is a higher concentration of greenhouse gases. We have available some climate models which are practically the solution of the equations of motion for a long-term time scale. And these climate models that include solar radiance changes cannot reproduce these observed temperature trend over the past century or more without including a rise in greenhouse gases. So that means that this increase of temperature, especially in the last around 100 years, cannot be explained only in terms of the changes of the solar radiation. In fact, solar radiation doesn't explain at all the changes of solar radiation doesn't explain at all the increase of the sea surface temperature, of the Earth temperature, in a lower atmosphere. So the only way how to explain this is to include into the model the increase of the concentration of the greenhouse gases. And this is the confirmation that there is a rise of greenhouse gases in the atmosphere. Obviously, one can say, okay, but the greenhouse gases changing also at a long time scale in Earth history before 19th century, but never at such a high rate as it is happening now. So here is this is exactly what I was talking to. This is the carbon dioxide level, which is one of the greenhouse gases, and which here you have the graph which shows how these greenhouse gases are changing with time in the last 800,000 years. How they get these data, because we don't have the measurements of that. They get these data. What they are doing, they are looking and analyzing the small bubbles which are trapped in the ice, in the polar ice, and these bubbles which are trapped, they maintain the exactly the same concentration of atmosphere which were at that time. So by determining the age of that ice and determining then the concentration of the concentration of the greenhouse, the carbon dioxide at the time when the bubble was trapped, we are able to reconstruct the time series of the carbon dioxide as one of the main greenhouse gases for a very long time scale, for a time scale on the order of almost 1 million years. And you can see that the greenhouse gases, first of all, they are changing. They are not constant. It's not a constant line. It changes, and there is also slight trend of increase. And you can see that there are some period where when the greenhouse gases were increasing very fastly, and also there are periods where they were decreasing very fast. You can see, for example, around 400,000 years, there is a strong increase and then a strong decrease and so forth. So you can see that there are number of peaks in the greenhouse gases concentration. However, something strange happened after around 19th century. You can see this strong jump of the carbon dioxide concentration in the last 100, 200 years, which is this thing here, and it reached more or less the current level. More or less, it reached the current level here, which is much larger than any other concentration of carbon dioxide in the Earth history of the last almost million years. So that's another important evidence that something strange is happening in the concentration of the greenhouse gases, which are, as we said, which should be responsible for this continuous increase of the Earth's surface temperature. And this is due to this high concentration, high level of carbon dioxide concentration, which has never been observed before, at least in the last million years. Temperature anomaly in the last 2,000 years is this thing here. You can see this temperature anomaly with respect to the average, and you can see that in the last 1800 years, more or less, there is a continuous, constant decrease of the temperature anomaly, with obviously with some strong oscillation around this average decreasing trend. But what happened now, put into the context of the last 2,000 years time series, is this sudden increase over the last 200 years of the temperature concentration. Okay. So there are key messages of these few slides. One is that sea surface temperature in European seas has been increasing in the past century at a faster rate than the global ocean. This is something what is not for this one here. This is the temperature anomaly over the entire globe. Here we are talking about something else. Another aspect is, which is also very important, as at a regional scale, at the scale of European seas, there has been an increasing rate of change of the temperature at the faster and faster speed, stronger, faster rate of increase of temperature than at the global ocean. So European seas are heating faster than the world ocean. the rate of increase in sea surface temperature in all European seas during the last 25 years is the largest ever measured in any 25-year period. It has been several times faster than the average rate of increase during the past century, and it is also much faster than the global ocean. This is something what is said in the first key message. Globally, average sea surface temperature is projected to continue to increase, although more slowly than atmospheric temperature. Here, why is this so? It's so because we have seen before in our discussion of the global conveyor belt that if we put in a sea the signal, which represents the increase of temperature, decrease of temperature, increase of salinity, or decrease of salinity at a certain place of the world ocean, for example, in a place where there is the main engine of the global ocean circulation, which is the northern Atlantic, sorry, there will be this trend of increase, and the signal will be traveling, will be doing the whole Earth path in about 1,000 years. Therefore, a globally average sea surface temperature rise should increase less or slowly than atmospheric temperature, because the ocean reacts much slowly than the atmosphere. The ocean, in other words, the ocean has much higher heat capacity than the atmosphere. Here is we put together the global temperature and carbon dioxide in the last more or less 150 years. There is a clear correlation or clear relationship between these two parameters. We have in the bold black line is CO2 concentration and the global temperature anomalies in global temperature in not anomalies but absolute values, but this time in degrees Fahrenheit. It's not, don't worry about that, but because we are not talking about the absolute value, we would like to consider the trend. So you can consider the trend, we can express this in any units. So you can see that CO2 concentration goes from 280 parts per million in late 19th century, reaching the 400, almost 400 at the beginning of the 20th century. These are the results of the measurements of the carbon dioxide. These are instrumental measurements, because what I showed you before the last million years, that was obtained from what we call proxies, from the concentration of CO2 in bulbs, in bubbles in the Earth ice. And here are the direct observations, because there is a long-term station which measures the carbon dioxide at Hawaii Island. And this shows the continuous increase in the last 150 years. And you can see that global temperature, global sea surface, global Earth temperature shows exactly the same trend. Shows the trend of increase, which becomes much faster in the last 100 years or something. So that's one thing. This is additional evidence that the global temperature and CO2 concentration, carbon dioxide concentration are related one to another, where obviously the carbon dioxide concentration is the cause of the global temperature increase. Okay. So we have the increase of the sea surface temperature. We have we have also obviously the increase of the atmosphere, lower atmosphere temperature, And as a consequence of that, we should have some additional effect, which is the sea ice losses. The sea ice losses are due simply to the increase of the Earth's surface temperature and lower atmosphere temperature. And here are some numbers which shows how much ice losses are due in the last years, and the ice covers 10% of the Earth's surface, and you see it seems that it is disappearing, and obviously disappearing very rapidly due to this increase of temperature. So we can see that the land glaciers we have like loss of 400 billion tons of total glaciers mass per year since 1994. So it's a huge amount of glaciers which has been lost, and the water from them is coming into the sea. We have also, at the same time, we have Greenland and Iceland loss of ice, which is about, at least, which is a little bit more than half of that. It's about almost 300 billion tons per year since 1994. Antarctic is losing half of that, approximately per year, which is about a little bit more than 130 billion metric tons. So altogether, ice loss at the Earth surface is like 900 billion metric tons per year, which is a huge amount of ice. And this ice, this water then ends into the sea. Okay, that's another important effect. The ice loss and the fresh water which is obtained from the ice loss is ending into the sea. And you will see what is the another consequence of this ice loss at the sea surface. Here is the one of the most important, since this water is pumped into a certain way, is pumped into the ocean. We consequently we have the increase of sea level, right? Because if you add the water into the ocean, the sea level has to increase. So here are some numbers due to this loss of ice. We have sea level rise by 2100 by the year 2100, which is predicted one, is like 45, half a meter of the sea level will rise in until 2100, year 2100. But due to the increase of the global temperature of 1.5 degrees, due to the increase of the 2 degrees Celsius, the sea level rise will be even higher. Obviously, higher is the sea level, the sea surface temperature increase, the higher is the sea level increase. In all this sea level increase, we will have a different contribution of different factors or different factors which affect this sea level rise. First of all, not the largest one is Antarctic ice sheet, which will contribute like a around 6 centimeters increase. Here, the -8 to +35 are the interval of between major and lower and higher estimate, because all these are estimates, so you have to take into account the error bars. Greenland ice sheet is contributing about 7 centimeters with the error bars between plus 30 and plus 19 centimeters. So the Antarctic ice sheet can contribute either of the lowering of the ice sheet or the lowering of the sea level or the increase of the sea level. Greenland ice sheet, loss of Greenland ice sheet will contribute only to the increase of the global ocean sea level. There is another important aspect of the increase of the sea level, which is what we call thermal expansion. What is the thermal expansion? Thermal expansion means that if you increase the temperature of the seawater, its volume will be increasing. The volume of the seawater will increase, and therefore, consequently, there will be an increase of the sea level. So the thermal expansion contributes like from about 20 centimeters, between 10 and 27 centimeters of increase of the sea level. So the sea level will be increasing due to thermal expansion more than ice sheet loss in altogether. Almost all the ice sheet loss will contribute almost equally to the sea level increase as the thermal expansion. Glaciers and ice caps will contribute to 11 centimeter in sea level increase, which is even that is larger than Antarctic and Greenland ice sheet loss. Then we have a land water storage. So sea level rise by 2300 would be 59 centimeters, or by 2100 it will be 48 centimeters. So wherever you stay now, if you stay half a meter above the seawater, you will be by 2100 you will be certainly almost underwater. That's a very important thing, because it will introduce the pretty large changes of the low-lying land areas, like the deltas of rivers. For example, the sand islands like Maldives will be completely underwater. So this is something which is really an important problem, which has to be taken into consideration. There will be what we call the ecological immigration, because the people will be escaping from the areas which will be ending underwater. So this is really an important problem for the humanity. We have to address. So all this research presented compares impact at 1.5 and 2 degrees. So the very strong and large scientific literature has analyzed these aspects, because obviously that's a huge problem for the scientific problem, and also the and political and economical problem. So can you imagine that a lot of scientific papers has been dedicated to this problem? For example, in total, around 150 scientific papers were identified, which are published around 2018, and which are discussing the sea level rise problem. And so this is something what I wanted to tell you, to what extent this problem is important in a scientific literature, in a science as a thing where science has to give as good as possible the responses, because you are not supposed to make a strong error in estimating the sea level increase. You are not supposed to give the too much sea level increase or too small sea level increase. And this can be done only by numerical models. And numerical models are not including all the effects. Is not able to include all the effects or the causes of the sea level increase in order to get a real good prediction. The models are obviously becoming more and more sophisticated, so as consequently the prediction of the sea level increase becomes more and more closer to what we should expect. Here is the annual Arctic sea ice minimum area. Here is that's why is the Arctic sea ice minimum. Arctic sea ice minimum because the sea ice in the Arctic changes on a seasonal scale. It's a minimum in summer and maximum in winter, northern hemisphere summer or northern hemisphere winter. Therefore, that's why you have these high and lows or a very high frequency, which are associated to the seasonal variability. Further, if you look at the average curve, if you draw an average curve of the variations of the Arctic sea ice minimum area and connect these, you obtain that there is a continuous decrease, but there are sudden drop of the sea ice minimum area starting from late 90s, and here is early 2000, and then there is some plateau. So there is no really a continuous decrease, but there are also obviously superimposed longer term variations. But generally, we can say that from 80s up to 2020, we have like a decrease of the Arctic sea ice minimum area, which is reduced to by 3 million kilometer cubic, all in these 30 years, which is a huge surface, which is now without ice in the Greenland. Greenland if you look at the Greenland means the green land. So that means that once upon a time the Greenland was not completely without ice. So that means that there are in the history of the Earth, there are periods when the Greenland was completely without ice. And at that time, obviously, the sea level was higher, but maybe the sea level was not as high as it will be by including the thermal expansion, because thermal expansion is very important. So even though the Greenland was without ice in Earth history, the sea level probably was not as high as it will be, or it would be, including the thermal expansion part. Here is the essentially the same graph, which shows the Arctic summer sea ice extent in the kilometer. This is the previous one, is a minimum area, and here is this is the same thing, which shows essentially it gives essentially the same message, where you see the average is this full line, and this dashed area is the standard deviation or the average. Here is another interesting graph, which I like it very, very much. shows the rate of change in ice cap height over the Greenland in centimeters per year. So in this thing here is applicable to entire summer sea ice extent, but it's not obviously the same all over the Arctic. If you look Arctic at some separate different parts of the Arctic, you will see that the rate of change of the ice cap in centimeters per year is not the same over the entire Greenland. The closer to the surface you are, the stronger is the rate of change, the rate of loss of the ice in this area here. If you are in the center of the Greenland, the rate of change is almost zero or slightly above zero. Why so? Because the seawater is warming up, and by warming the seawater, there is a stronger rate of loss of sea ice in the coastal area of the Greenland. As far as the Antarctica is concerned, there is this long-term trend is not clear. And if you remember, when I was showing to you the few slides ago, the Antarctic would contribute to a lesser extent to the increase of sea level than any other ice-covered areas. This is because of the fact that the Antarctic sea ice extent is smaller than the changes of the sea ice. Antarctic extent is smaller than, for example, the Greenland, or, for example, the glaciers, land glaciers losses. And here you can see this effect of the long-term changes of the Antarctic sea ice, mainly in the in the yearly minimum of the ice of the Antarctic. And here you can see that the line in 2017, more or less, there is a minimum of sea ice, in absolute minimum sea ice, ever since end of the 19th century. So but the signal is not so clear, is not so clear as in the Greenland. Yes. So let's see what is the long-term average increase of the sea level due to this thing, especially in the last period. This is something as I'm underlined many times so far. The most important role in that is the use of time series of satellite data to determine this last period increase of the sea level, because we have a very good coverage of the Earth, and we are able to calculate the rate of the sea level increase with a pretty high precision. So from 1992 to these days, to about 20 years ago, a little bit. This is the relatively old estimate, because here they are talking about 20 years. We are now already have 30 years of data, because we started 1992, so it's almost 30 years of data. But for the 20 years when this was calculated, the sea level was increased by 2.2 millimeters per year. And now the last years, these last 20 years, the last sea level rise is about 3.3 millimeters per year. So there is not only the long-term sea level increase over the last 20 years, but there is also an acceleration of the sea level increase. Moreover, 20 years ago, the seawater volume increase due to the temperature increase was contributed about 50% to the overall water volume. But now the heating contributes only 30%. What that means, this is a very important thing, is that the ice melting or ice loss, earth ice loss, is contributing more and more to the sea level increase. Okay, so as far as the sea level increase is concerned, the ice melting becomes more and more important with respect to the heating, because as you can see here is about 50%. The temperature increase contributed about 50% to the overall volume increase. But now the heating contributes only 30%, and the rest of the sea level rise is due to the ice melting. So this 3.3 millimeters per year, like 1 millimeter per year, is due to the heating, and the rest, about 2 millimeters per year, is due to the long-term ice melting. Okay, so this is another thing I will be talking to you about measurement techniques in the next few lectures. But here, not only from satellites, but also from land measurements of the sea level, we can see these sea level trend of increase. And these data are from the coastal sea level measurements, sea level tide gauge. We call tide gauge. We call these instruments which are measuring sea level at the coast. And you can see that also there, these measurements for the period 1870 to 2013 shows the clear trend of sea level increase. And you can see from the very beginning, when 1880 to 2020, 2015, we have like a 200 millimeters of the sea level sea level increase, which is about 20 centimeters, which is exactly what we have shown from satellite data. About 2 millimeters per year is the long-term increase of the sea level, which is confirmed both in the last 20-25 years from the satellite measurements, as well as from the coastal tide gauge records, from the coastal measurements. So you imagine that with satellite you have the whole ocean surface covered with data, while the coastal measurements are covered only the coasts where these instruments were available. There are not so many coastal tide gauges available along the world ocean coasts. And that's another graphical presentation of the sea level increase. And here you can see that this is another additional confirmation of the sea level increase. This is the average sea level over the world ocean. This is the and this essentially gives the same information. 3.2 plus minus 0.4 millimeter per year is the long-term increase of the rate of increase of the sea level in these 20 something years. And if you multiply by years until 210, until 2100, you get the terrified numbers. Obviously, the long-term changes of the sea level are not of the world ocean are not present at the same rate at all local in all regions, or locally you can have the higher and lower sea level increase because of the local oceanographic conditions and also geological conditions. Now you will see on an example of the Venice Lagoon. Venice is and one of the examples of the areas which will be very much endangered by the sea level increase, because the Venice is the city which is typically on the order of a meter above the sea level. Therefore, it would be very endangered by the increase of the sea level on this long time scale. I hope you will have chances, or you already have chances, to visit Venice. It might not be you won't have chances to see the flooding of Venice due to this high sea level, but this is another very, very important phenomenon which is endangering the city of Venice as a cultural heritage of the earth. Here you can see the long-term sea level record from 1870. This is and so in Venice we have more than 150 years of a sea level record from the tide gauge instrument, which are a number of tide gauge instruments installed in the Venice Lagoon. And what it gives also here, it has this increase of the sea level in the Venice Lagoon. It goes from 1870 to 2010. You have here the sea level increase of about half a meter. So the sea level has increased in the Venice Lagoon, in a city around the city of Venice, which is on an island, by half a meter in these 150 years, which is very, very important number. So let's see. However, let's see why is such a strong increase of the sea level in the Venice Lagoon, because it's not. In the world ocean, it's not such a strong rate. So let's see. Oh, here is a part of this explanation. This is in red is the sea level changes in the Venice Lagoon as measured locally in the Venice Lagoon. Here is in blue curve gives the sea level measurements in Trieste, and you can see that up to 1940, for example, or 1930, the Venice sea level and the Trieste sea level were changing more or less parallelly. So you don't have the changes in the rate of increase of the sea level in Venice and in Trieste up to 1930 or something. So that means that both Venice and Trieste, they showed clearly the sea level increase due to the global sea level increase. However, at a certain point around the early 19th century, there was this there is an acceleration of the sea level increase in Venice with respect to Trieste. So assuming that Trieste is reflecting the global sea level increase, that means that there was some mechanism which is present, or some which is affecting the sea level in Venice Lagoon, which is not present in Trieste. So when the people were going to look for these differences in Trieste and Venice, they found out one important aspect which makes the sea level increasing the Venice Lagoon faster than in Trieste. And what is this? The fact is that around early 19th century, there was the construction of the industrial area behind, in the coastal area of Venice, and this was in city of Marghera, which is behind Venice and the land. And so what is happening that for this industry, they need the water. They need a large, huge amount of water. So they're pumping the water for the underground of the Venice area. By pumping the water for the underground of the Venice area, using this water for industrial purposes, so that the land was sinking. So you have the sea level. On one hand, shows the increase of the sea level. On the other hand, shows the subsidence, the sinking of the bottom of the land in the Venice area. So you have the sea level is increasing because the sea level increase of the global ocean, and on the other hand, there is the subsidence of the land in the area. So some of these two has been manifesting in the apparent increase of the sea level in the Venice Lagoon. The result is exactly the same. You're sinking of the city of Venice or increasing of the sea level gives the same effect. So when they understood this, they stopped pumping this water around the 60s. They stopped pumping this water, and you can see that right after that, the sea level reached a plateau. Which went on until 1990, and then started again to increase, parallel to what is happening in Trieste, where this land subsidence was not present. So you see that the local conditions, the local geological or the local conditions of activities of man can influence the sea level changes or the sea level rate of increase even higher than it is on the global ocean. So this is the illustration. This is the Venice. This is the city of Venice, which is on the island. You can see the island. This is the island. It's like a fish. And here is the Canal Grande, which is the main traffic, the main traffic street, the main channel which connects different parts of the Venice. And what this area shows what part of the city of Venice, of this island, is underwater when you have the high sea level, because what is happening really in Venice? In Venice, you have the increase of the sea level, but the city of Venice, in normal conditions, if I may say, normal conditions, when there is no local increase of the sea level due to the wind influence or due to the low atmospheric pressure, in that case, the sea level, the Venice city is above the sea level. However, when you have the low atmospheric pressure means the higher sea level. The less the atmospheric pressure push the seawater, the sea level is higher. So in the weather conditions, remember weather conditions, not the climatic conditions, but in the weather conditions when the atmospheric pressure is lower, the sea level in the Venice Lagoon is higher, and the sea level in general is higher, but in the Venice Lagoon is even higher. And this is one component. The other component of the flooding of the Venice is the associated the wind. If you have the wind blowing along the Adriatic toward north, it's pushing the water northward, so it's causing the increase of the sea level. So you have the increase of the sea level due in some specific weather conditions due to the wind blowing from southeast and the low atmospheric pressure. These two factors are contributing to the high sea level and result in the flooding of the city of Venice. And so if you have the sea level higher than 100 centimeters above average, for the sea level of 120 centimeters, there are some only very few areas which are under the seawater, which are this thing here is the Piazza San Marco, which is the main square of the city of Venice. And for 140 centimeter mean sea level above the average, you can see that a huge number of Venice is underwater, these bluish areas here. If you have this is at the beginning of the last century, it's 1908. In 1996, so this is the last years of the last century, you can see that already with a sea level of 120 centimeters, which is the huge part of the Venice is underwater, and already for the sea level higher than 100 centimeters, Piazza San Marco is under seawater. So you can see simply by looking at the colors, you can see that how worsened was the situation as far as the flooding of the Venice is concerned. Okay, this is how the people would walk when there is a high sea level. Where is the flooding of Venice? They have these this kind of boots, what they use to kind of walk on Venice. But the fact that they're using this could be avoided with a new situation, with a new huge project which has been launched like 20 years ago in Venice, is this thing here. What they build dams at the opening of the Venice Lagoon. So Venice Lagoon has 3 openings where the Venice Lagoon communicate with the open Adriatic Sea. And so somehow, when there is the prediction that high sea level or high seawater is coming, the lagoon should be closed in order to avoid that the water enters the lagoon. So there should be a possibility to close these 3 openings at the Venice Lagoon and prevent the increase of the sea level in the lagoon, and prevent the possible flooding of the Venice, because this flooding of Venice is damaging the base of the city of Venice, and so there are a huge amount of damages to the city of Venice due to this flooding. And what they constructed this these dams, which are constructed in such a way that you have in a normal situation when there is no high sea level prediction, when the sea level is not high in these weather conditions, but there is no low atmospheric pressure and southeasterly winds. These dams are at the bottom. They are fixed here, and they are at the bottom because they are full of, these are big reservoirs filled of water. Once there is a prediction that there is a high sea level is coming, or the flooding is coming, the water from these reservoirs were pumped out of them, and due to the buoyancy, they are lifted up. So this is how they look when they are appearing above the sea surface. So this is how we are fighting the sea level increase in this specific case. Every country or every local situation is different. Therefore, every situation has every local every places has their own solution. This kind of solution, or generally building dams, is something which is developed in Holland coast, Dutch coast is very low-lying coast. There are dams on the Thames River in England. Wherever you have these weather conditions which stimulate the flooding, you have to build these dams. And I'm talking about the weather conditions, but on the long-term time scale, this dams has to address these long-term problem. And these dams, which are now in Venice Lagoon, they started to function this year, the last November, and they demonstrated that they are very efficient in blocking the entrance of the huge amount of water due to the increase of the increase of the sea level in the Adriatic. This situation. Let me see. Okay. In order to see what is the frequency of these weather conditions when the sea level is high in Venice, where the sea level is higher than 110 centimeters above the average sea level, we have made statistics by different months. Sorry for Italian, but you should understand some Italian because you are already for some time in Venice, in Italy. We have done they have been doing the statistics of these high sea level or conditions, weather conditions, such that generate the high sea level, and you can see here that most of these situations appear in October, November, and December in autumn period. So in autumn period, these frequencies of such weather conditions are the most favorable for the instantaneous sea level increase are present in autumn period, and therefore June, July, and August, practically this situation doesn't appear at all. So that's how it looks like as a seasonal changes on the high sea level in Venice, of the flooding event in sea level. Here is another interesting graph which shows the frequency of the high tide in Venice as a function of time, starting from the beginning of the last century up to nowadays. And what you can see is the increase of the frequency of these high tides with time since the beginning of the last century. Why is this so? This is so exactly due to this fact that the mean sea level has been increasing in the Venice Lagoon due to the global sea level increase and due to the local subsidence of the land in the area of Venice. And so due to this thing, the sea level has been increasing, and therefore the tides, which are higher than 100 centimeters, are more frequent now than they used to be. That's the illustration. What is how the how the long-term increase of the sea level causes the increase of monthly frequencies of the high tide in Venice. So we hope that this kind of boots will not be used anymore, but we will see next winter, next November, next October, next November, and next December. Another thing is that that the sea level is not only changing locally because of the activity of the industrial activity, or in general of the anthropic activity. But the sea level variations are changing locally also due to the changes of the circulation. Here is, for example, here is an example how the sea level in the Mediterranean varies differently on different parts of the Mediterranean. Here is you recognize already the Mediterranean, I hope so. You are here right now, there's Trieste, the Venice is here. This is the Adriatic, and this is the Gibraltar, which connects the Mediterranean with the Atlantic. And here is the long-term trend, the trend obtained for the period 1999 to 2006. It's a relatively short period if you want to talk about the long-term changes of the sea level. But anyhow, it illustrates very well that this sea level increase is not homogeneous over such a small area as the Mediterranean. The Mediterranean is a relatively small area with respect to the global ocean. And you can see that not only that if you do the integral over the entire Mediterranean, you will have the sea level increase. Certainly you will have obtain the sea level increase even in the period, in this small, relatively short period, 1999-2006. But on a smaller scale, in smaller parts of the Mediterranean, you can see that you can have even a decrease of the sea level, like it is here. This is the Ionian Sea, and you have these sea level decrease of 15 millimeter per year in this period here. But on the other hand, next to this area here, this is the Levantine Basin, you can have the plus 15 millimeter per year of the rate of increase of the sea level. So you can see that one thing is the average, the spatial average for over the ocean or over the large world ocean. And another thing is how these sea level rate of change varies on a smaller time scale. You cannot even see here the Venice Lagoon, the sea level increase stronger than for the rest of the Adriatic, because this is the very, very small, tiny area with respect to the Mediterranean, or even more than the global ocean. To what extent this impacts the long-term sea level increase of the Mediterranean, or even less on the scale of the ocean. Why is this so? This is due to the sea surface circulation variation, because you remember when we were talking about the sea surface circulation, the geostrophic balance, when we have the changes of the sea surface circulation, we do have the changes of the sea surface slope. Okay, so that means that any change of the sea surface circulation, any change of the circulation, induces the changes of the sea surface. Therefore, these are signs that here in this specific part there were changes of the circulation such that they invert the global sea level rate of change. This is one thing. The other thing is that if you have the transport of the dense water, for example, in this part here, what you would have the sea level decrease, because the higher is the density, the lower is the sea level. So any type of transport, any type of changes of the circulation in the world ocean reflects on the sea level variation. However, the sea level variations, independently of all these factors, the prevailing factor which induce the long-term variations of the sea level are the ice melting and the thermal contribution, the sea level, sea surface temperature. These two factors are determining the long-term positive long-term rate of sea level increase. The other factors can induce different rate of change of the sea level, but on the global scale, they don't contribute to largest extent, okay? So that's one example how the sea level variation can change on the local scale, both in a very micro locations like Venice Lagoon and in the local scales like on the Mediterranean. The long-term changes of the sea surface temperature or the temperature of the ocean can introduce also changes on the biology, on the ecosystem of the ocean. Why so? Because if there is an increase of the sea surface, of the temperature of the ocean, there should be an increase of the species of the organism which are present in tropical areas or which are present in warmer seas, and they would find a more convenient environment, and there would be the increase of the biological component of the biology or the organs which are present in warmer seas. Let's see one example of this thing. You have heard last few days or last week, you have heard a lot of Suez Canal. Suez Canal, which is the main passage between the Red Sea and the Mediterranean. It's important commercially, obviously, but you have noticed last week where there was a ship which blocked the passage of ships across the Suez Canal, and then there was this complete block of the traffic, like 400, 500 ships were blocked in the Suez Canal because they couldn't pass. But that's the commercial part. Let's look at the oceanographic component of the fact that this canal exists. This canal exists since 19th century. It has been built in order to connect the Red Sea and the Mediterranean in order to avoid the large trip of ships around the Good Hope Cap of Good Hope in order to reach the Mediterranean and vice versa. But from the oceanographic point of view, it has an interesting and important aspect. This Suez Canal connects really the Red Sea and the Mediterranean. By connecting the Red Sea and the Mediterranean, it represents it's not only the traffic of ships, it's traffic of organisms between the Red Sea and the Mediterranean. So the tropical organisms which are present in the Red Sea can reach the Mediterranean and stay there under certain conditions. These tropical organs which are present in the Red Sea, once they reach the Mediterranean, they found themselves in a specific environment because there is no natural enemies which would reduce them, because every organism has its natural enemy which keeps its population at a certain level. Only man doesn't have natural enemies which would keep the population under a certain sustainable level. Sustainable level means that population of living organisms is not such that it will endanger the rest of the ecosystem. In our case, in the case of humanity, it's not really such a situation. So that is why we started with in the beginning of the last century with a few billion of people, and now we are almost at 7 billion of people. So that's the huge increase of the human population, which certainly introduce the disequilibrium in a global ecosystem. But let's forget about this. Let's keep with oceanography. So these organisms which are coming once in the Mediterranean, they don't find the enemy. They don't find the natural enemy, so they start growing. Their population starts to grow. They would start even more to grow if the temperature is similar to the temperature of the sea where they come from. The Red Sea is a subtropical environment, with the temperature is higher than in the Mediterranean. Therefore, if the temperature in the Mediterranean would be or higher, they would even grow and multiply even faster than in the place where they come from, in the Red Sea, because they wouldn't have the natural enemies. So and what is happening with a long-term increase of temperature? Long-term increase of temperature of the ocean brings exactly this type of conditions to the organism coming into the Mediterranean. They would find the higher temperature. They would find the temperature which is closer to what they get at their origin. But in addition to that, they wouldn't have the enemies. So they would grow. They would find, like at home, even better than at home, because they would grow without any limits. And in fact, indeed, this is what is happening. We have a whole series of what we call reception species. Reception species are called by the engineer who did reception. Lesseps is the engineer who projected the Suez Canal. And reception species by him is called the species which comes from the Red Sea, enters the Mediterranean, and remains there and lives there. So you have these few species which, since I'm not a biologist, but I give you just these examples, which enter into the Mediterranean, stay there, and multiply there because they found a relatively good temperature for them to live, and they don't have enemies in this specific area. So this is very interesting phenomena which is appearing as a secondary effect, but very important effect of these long-term changes of the temperature. Yeah. Now we have to open another chapter of these long-term changes of the global ocean climate change, and so I would prefer to stop here and talk about the next time. I would like to talk to you about the world ocean circulation and how these world ocean circulation will be changing in a function of the changes of the long-term changes of the sea ice melting, of the increase of the seawater temperature, how these things would affect the global ocean circulation, and what would be then as a consequence of all of these on the global climate. So we have on one hand, we have the sea surface temperature increase. We have the lower atmospheric temperature increase. We have the ice melting, glaciers melting, increase of the fresh water in the ocean. And all these then impacts the global ocean circulation, which on its turn impacts the global climate. So you can see that how all these things are connected. And also, at the same time, this global ocean, climate change impacts the ecosystem itself in the ocean, as we have seen on a very simple example on the Suez Canal. Okay, so that's it, and I would like to stop here. And I'll see you the day after tomorrow with the rest of this climate change lecture, and then we pass to the final part, which is the instrumental measurements. Yes, and now interrompi condivisione. Okay, so have a good time and see you the day after tomorrow.
Thank you.
Bye bye.
Thank you.
Bye.